here that insert study of CO insertion or rolling silicon catalyst.
Thank you, Chairman. Thank you very much. I'd like to acknowledge the co-authors, Rich Srinivans and Mike Polagos, for providing the experimental data and sharing this slide here. And I also like to thank the NSF for providing me the table grant here and Professor Solimir Moses giving us this opportunity to present my work. Next slide, please. Next. Oops. Insertion into the metal alkyl bonds is one of the most widely studied reactions in organometallic chemistry. And this reaction has been found to occur on various types of these transition metal complexes. And the interest in the CO insertion is derived from the fact that this reaction provides a pathway for the conversion of olefins or other substrates to the oxygen-containing species, which is a very high value compared with the original reactants. Next, please. And that reaction has been well studied in organometallic reaction. And homogeneous catalytic reaction in modern CO insertion include a number of reactions. And there are just a number of examples here is the hydroformylation, methanol carbonation, CO hydrogenation to ethylene glycol at a very high ratio. And what we are really interested in here is hydroformylations. And there are two reasons why we study the hydroformylation. The first one is this reaction has often been used as a probe reaction to determine the CO insertion activity of this C2 oxygen synthesis catalyst. So understanding of this reaction will provide a better picture of how the CO insertion takes place on the supporting metal catalyst. And the second reason here is this hydroformylation can take place on either supporting metal catalyst or metal complex. So understanding of this reaction will provide a link to bridge relationship between homogeneous CO insertion and heterogeneous CO insertions. Next, please. Okay, so first of all, I'd like to do here is to provide a brief background about the hydroformylations. The hydroformylation is a reaction of the same gas with argon to form aldehyde. The reaction was discovered by Rowling in Germany in 1938 while he was studying the Fischer over the cobalt catalyst. And later he found the cobalt carbonyl generated from the cobalt metal surface indeed is more active than cobalt metal for the hydroformylations. And these cobalt carbonyls and later the development for the rhodium carbonyls, and now the cobalt carbonyl and the rhodium carbonyls and their modified complex has been used for the commercial hydroformylation process. Next, please. And this hydroformylation, the mechanism of this homogeneous hydroformylation can be described by these four steps here. The first step is the activation of the carbonyl to form the hydroxide carbonyls. Second step is the formation of the alkyl metal complex. The third step here is the insertion of CO to form the alkyl complex. And the last step here is the hydrogenation of this alkyl species to form the aldehyde and the regeneration of the initial parent species here. And this is the step we have been really interested in. Next, please. So let's take a look at how this CO insertion takes place. Okay, it's pointed out by the Professor Ishikawa, the insertion takes place indeed is through a migratory CO insertion. And how this migratory CO insertion occurs is here. This alkyl group migrates from the metal to the carbon end. Now this alkyl, which is attached to the metal, which is migrated to attach to the carbon end of the CO and to form the alkyl species. And this has been proved in the homogeneous catalysis. In the homogeneous catalysis, there's only one type of CO here, the migratory CO insertion. This type of CO you can classify as a terminal CO or linear CO. However, on the heterogeneous supporting metal catalyst, for example, on the loading catalyst, CO can absorb in various ways. One is bridge, one is linear, and gel-dicarbonyl, or there's also possible linear CO. CO may absorb in the linear form on loading class site. And what we have been trying to do here is to identify the type of CO involved in the CO insertion to form the archetype. Okay, there's one thing I'd like to point out here. In homogeneous catalysis, the CO insertion is a very selective process. Usually you can get more than 99% selectivity for water archetype. But on supporting metal catalysis, this metal is very active for hydrogenation. So most of the time we produce the FN, more FN than archetype, except at very high pressure conditions. But again, at a very high pressure condition, part of the loading may form the carbonyl, which catalyzes hydrogenation. So what I'm going to do next is to show you how we identify the species for the CO insertion on the supported loading metal catalyst. Next, please. Okay. We have been using the infrared spectroscopy. This is our infrared cells. Let me quickly go through this cell here. This cell consists of 4 pieces of fringe with 2 calcium fluoride window. And this is a step window. The reason we use the step window is to minimize the gas phase species in the reactor so that we can primarily see the adsorbed species. And the catalyst, we take 20 milligrams of catalyst and place it in the form of very thin disc to place in the reactors. And in order to do some reaction study to produce more product, we also take another 30 or 40 milligrams of catalyst and put it surrounding in the disc so that we can produce enough product for mass spec analysis. Next, please. Okay, this is a result of a reaction of the ethylene with hydrogen, reaction of ethylene and hydrogen with the adsorbed CO on the reduced loading catalyst. Okay, let's take a look at this infrared spectrum here. Absorption of CO on the reduced loading produced linear CO band, bridge CO band, and gel-dicarbonyl band. And this is a reduced loading on silica. And the crystallized size of this catalyst is around 92 angstrom, determined by X-ray diffractions. An exposure of this adsorbed CO to ethylene and hydrogen caused the decrease in the intensity of the linear CO and the formation of the aldehydes, propional aldehyde species. While other species such as bridge CO and gel-dicarbonyl species remain about the same. And certainly there's hydrogenation take place here. And a lot of the span are the CH vibration of the FN species. So from this result we conclude the linear CO on reduced loading participate in the CO insertions. Next please. Okay, similar study has been also performed on the oxidized loading catalyst. And that result has been presented in the Budapest. So I just want to quickly summarize here. This is a different spectrum. From the different spectrum, we conclude the species which exhibit the band at 2106 is a band responsible for the formation of the aldehyde species. This is a different spectrum, all right? And so from this result, we conclude linear CO on loading class can also act as a precursor involving in the CO insertion leading to the formation of the aldehydes. And we found, in fact, this loading class is more active than loading 0 for the CO insertion. Next please. So from this result, we know that bridge CO does not participate in the reaction and linear CO involved in the CO insertion. In order to increase the selectivity for the formation of aldehyde, it's very logical. One of the logical ways to do it here is to block the bridge CO side. And there are several ways to block the bridge CO side. One way is by adding the additive. So we add a silver here as additive in the catalyst. When we add a silver, this silver can form the several crystallites, and some of the silver can also disperse on floating catalyst. And this spectrum here is basically derived from the extensive catalyst characterization by using the XPS and IR and the SN hydrogenalysis. And as you can see here, the increase of the silver content decrease the ratio of bridge to linear. The ratio of bridge to linear CO. So this is clearly indicate part of the silvers located on surface of loading and block the bridge CO site. Next please. And let's take a look at the in-situ infrared study here. Okay, this infrared spectrum and GC result was taken at the same time. As the silver content increase, this is the result of the in-situ infrared study at 10 atmosphere, 20 atmosphere. As we increase the silver content, the ratio of the linear to bridge CO increase. As you can see here, at a high silver content, the bridge CO is not intense, so we can actually see the ethylene band here. At low, if we don't have silvers, then we'll see this intense bridge CO here, which is overlapped with the ethylene band. So increasing the silver content increase the ratio of linear to bridge, and also increase the selectivity to the aldehyde. And this is what's determined by the gas chromatography. The next please. Bridge CO site can also be blocked by the additives such as sulfur. So we add the sulfur by passing the hydrogen sulfide over through this catalyst at 240 degrees. And this reaction again was conducted at 10 atmosphere. So we see the bridge CO here again was suppressed, so you can see there's a clear ethylene band here, and additional sulfur increased the rate of formation of propenoaldehyde and suppressed the formation of the ethane. So this result will conform the linear CO is a species involved in the CO insertions. Okay, so this result here was conducted at high pressure, so we can clearly see there are aldehyde band and linear bridge and extended carbon hydrogen switching band of ethylene species and additive species. And one of the questions that's often been raised in the in-situ infrared spectroscopy study is the species we observe in the infrared spectrum media spectators. So we have tried to combine the in-situ infrared technique with isotopic transient technique, which has been proposed by the Professor Tamaru a long time ago, and to study this reaction. Next please. Okay, this is our experimental apparatus for studying the hydrogen formulation. Okay, this is the infrared cell. We use the in-situ infrared reaction study, and we add a switching bar here to switch the linear, to switch the gas phase C12O to C13O, while maintain other reactant flow at a constant flow rate. And we use the in-situ infrared spectrometer here to record infrared spectrum at a rate of 3 scans per second. And the response of the gas phase species is monitored by mass spectrometers. Next please. Okay, we have used these techniques to study the loading, cesium formaldehyde loading catalyst, and this catalyst has been extensively studied by Professor Kinnaman, and we followed this method to prepare this catalyst. So this catalyst, before the switch, okay, this reaction was conducted at 1 atmosphere, 240 degrees. We didn't conduct it at 10 atmosphere because it's very expensive to send the 10 atmosphere pressure of the CO through a reactor, and we have been doing that by pulse. So here I'm going to only present the switching at 1 atmosphere at 240 degrees over this gas. And the loading is 5% and cesium is 5%. Okay, before the switch, we see the linear CO band and the bridge CO band and the band at 1684, which has been assigned by the Professor Kinnaman as a PLD CO and by also the Professor Ishikawa. And the switch from the linear from C12O to C13O causes an immediate switch of the adsorbed species, except the species in this range. And the replacement of the C12O by C13O on the surface was accomplished within the 0.41 minutes. This is unit of minutes here. And this species here, which has been assigned to the Oxley species, remain the same. So this indicates species here are due to the spectators. However, we are not able to determine whether these species are really involved in radiation, but we are pretty sure this may not be a spectator at all. Okay, next please. And here is the gas phase response. Okay. The argon was aided with the CPLO to determine the effect of the flow patterns and the gas phase fold out on the response. So CPLO is not shown in this figure here, and this is the response of C13O, and you can see the CO2, C13O2 follow the CPLO very closely. So this indicates without radiation also take place on the surface, and which is a very fast reactions. And propenoaldehyde is also formed as we switch from C13. Propenoaldehyde is also formed as we switch from CPL4 to C13O. The area above this response curve can be used to determine the residence time of this intermediate. So residence time of intermediate leading to aldehyde is around 0.35 minutes, and residence time for the adsorbed CO during the reaction is determined to be 0.05 minutes. Okay. Well, we have conducted the same study on the loading catalyst without the cesium to determine this effect of the cesium promoter. Next please. Okay, so this is the same study on the loading catalyst, which shown again the CO during the switch, CO come out, C13O come out, CO2 also follow the C13 very closely. However, in this case, the propenoaldehyde come out much faster than the propenoaldehyde from than the formation of propenoaldehyde on the cesium promoter catalyst. And as you can see here, the residence time for the intermediate leading to this species is only 0.414 minutes. So cesium appear to cause the catalyst strongly interacting with the propenoaldehyde species. Next please. And we have used the same technique to study the combinations. Okay, so this is the switch of CPL4 to C13, and we also find out the medium-rich CO switch within the 0.14 minutes. The switch is completed in the 0.55 minutes. Next please. And this is the gas phase response of the product, and we found out the methane is slowly evolved as we switch from C12 to C13, and again CO2 is the response of CO2 is much faster than the response of methane. Okay, next please. So here I have to summarize my talk. We found both loading ions and loading zero are the sites which active for the CO insertion. And it appears the loading process is more active than loading zero. And the selectivity of the selectivity for CO insertion can be enhanced by blocking the CO site, rich CO site by aiding the silvers or sulfurs and other species. And the species we found exhibiting effect in this range seems to be a spectator species. And we also determined the residence times for these intermediates, for the formation of this intermediate under the same conditions. We found out the cesium homology catalyst gives a large residence time for the intermediates, and the intermediate for methane formation is significantly greater than the residence time for the formation for the intermediate leading to the aldehyde species. Thank you.
Thank you very much for your interesting contribution. Please, lecture is now open to discussion.
Just a small comment, in fact. As you know, rhodium silica catalysts are also good for acetic acid formation.
Yes.
And one of the work for acetic acid formation from rhodium catalyst with a very high ratio carbon monoxide to hydrogen equals to NAP, it was found that there is also an increase of acetic acid formation when they feed H2S in the flow. So probably it might be good to...
Yeah. We did look at those kind of experiments when I was a graduate student, and at high ratio of CO to hydrogen, a lot of acetic acid and ester is produced. So this is the transient study was done at 1 atmosphere, so we don't see acetic acid. And we are trying to add a lot of ethylene. So that CO hydrogenation reaction will sort of suppress a little bit. Yes.
If I understand facility, the effect of cerium in your case seems to enhance the residence time of your alcohol.
That's right, yeah.
Did you also look for alcohols in your case?
No alcohol was produced.
No alcohols.
Yeah, it's all aldehyde.
Okay. Second question, from other work, we know that cerium oxide also has a strong interaction with CO2. So one would expect that in your filter experiments, you would also expect a longer residence time for your CO2.
But it didn't. It didn't in our case. We didn't see that the CO2 response is as fast as the CO. Right here. How to turn this on? So this is exactly the same picture. The CO2 come out as fast as the CO.
So
I don't know why.
I think maybe I have suggested this. Maybe under your condition, your cerium is completely carbonated, and your temperature is so low that you will not dissolve the decomposed carbonate.
Yes, you are right, because we do see this yeah, I think your suggestion is right, because that's what we thought too, because we thought this carbonate species in this range is remain there, even when we switch.
So then it becomes more interesting to know what happens to your aldehyde. If your cerium is completely blocked with carbonate, how would your carbonate affect your aldehyde?
That's what we don't know, yeah. Our data is not able to show how the carbonate affects the aldehyde formation.
It's interesting.
Yeah, but we are performing the reaction study at high threshold so that we can produce enough aldehyde band. And this study is done by cost. And we didn't get the time to organize the data to present it to you.
There is arguments about the oxidation state of rhodium active for the hydroformation.
Yes.
And it's obviously these are also advantages. For instance, in the British rhodium catalyst, charging the rhodium 1+.
Yes.
Almost the same resemble for the surface between rhodium carbonate
Yes.
and heterogeneous
Yes.
situation. So, I'm some interested in the point that you apply the gold silver in this kit and modification of the rhodium surface and ask some event on the hydroformation. So you claim in the rhodium, isolated rhodium is an active for the
Yes.
hydroformation.
What? Yes, and rhodium plus is also the active side. Okay, now I'd like to point out that that paper is going to be published, it's going to be appearing in Journal of Policy in 3 months. We did add samples on the loading, and we found out when SIBO ratio to loading ratio at 1:1, that catalyst give the loading plus by XPS at room temperature and vacuum condition. But under the reaction condition, we does not see the loading zero, because under the high temperature you only see the medium bridge. So we weren't sure whether the loading process exists under the reaction condition or not. But we are pretty sure there's linear CO there, and there's high linear to bridge CO ratio. But if we determine the oxidation state of surface by XPS at room temperature, we do see some loading plus on SIBO loading gas with 1:1 ratio.
But at high temperature, the CO reducing the loading one without normalization occurs.
Yeah, you couldn't see it in the IR. Even if it exists, you won't see it either.
You can plot up, if you like, the decay, the rate of decay of the 2033 band, and as a function of time. I don't know whether it has the first order time dependence or what. But the question is you're virtually working with a static system. You mentioned that you could look at these mass spectrometer. Do you get something comparable rates of product production? In other words, can you relate the rate of the reaction to the rate of decay of living species?
The CO species.
Yeah.
This is a thing we have been trying for more than 6 months, and we haven't decided what to do yet, because either we can take the intensity or take the integrated area. There are two ways to do this. And it's hard to do a decomposition because the isotope has coupling effect and which tend to change the intensity. So what we have been trying to do now is just determine when the exchange process started and when the exchange process stopped. And we have been trying to determine, take this intensity and how to determine how this decreases. The whole problem here is we need to do extensive calibration to figure out the surface coverage of the CO which gives this intense band. So the most difficult part is to do the decomposition. And we haven't figured out a better way to do it yet. So I would like to have your suggestion.
Kind of like our Huizinga was doing before, where you normalize the initial.
Yeah, this can be done. But based on the isotope effect, that the two isotope, the second isotope species will change. We have done that already, in fact.
Yeah, I suppose you take the decay rate against the production rate of product.
Yeah, we have done that, but we hesitate to present that result because of the isotope interaction of which changes the frequency of the band.
Relatable? If you swap one against the other?
Yes.
Thank you very much.